For the first topic, we are going to discuss significant figures. This discusses rules to identify significant figures in digits. Rule number 1. All non-zero digits are always significant. For example 1, there are 5 significant figures because it is all non-zero digit. For example number 2, there are only 4 significant figures because the first digit is 0. As the rules state, all non-zero digits are the only significant numbers. Rule number 2. All zeros in between non-zero digits are always significant. I may have said that only non-zero digits are the only significant figures for rule number 1, but there is also circumstances that 0 is also significant. For the first example, there are 8 significant figures because there might be 0, but it is between non-zero, so it is considered significant. For second example, there are 6 significant figures because there are 2 zeros in between non-zero digits. But the first 0 is not significant because it is not in between non-zero digits. Rule number 3. All zeros before all non-zero digits are not significant. As I have said for rule number 2, the first 0 is not significant because it is not in between non-zero digits. Example 1. There are only 4 significant figures because the first few digits are all 0. Only 7, 2, 5, 8 are significant because it is non-zero digit. Example 2. There are only 5 significant figures for the same reason. Only 9, 3, 6, 8, 2 are significant because it is non-zero digit also. Rule number 4. All trailing zeros to the right of the decimal point are always significant. Example 1. There are 5 significant figures because the 20 is a trailing zero. 9, 5, 4, 0, 0 are all significant except for the zeros before non-zero digits. Example 2. There are 6 significant figures because there is a 0 in between non-zero and the last 2 digits are trailing zeros. 2, 5, 0, 9, 0, 0 are all significant. Lastly, rule number 5. All zeros that act as placeholders are not significant. It is zeros after non-zero digits. Example 1. There are 3 significant figures because the last 2 digits are placeholders. Example 2. There are only 2 significant figures because the last 5 digits are also placeholders.
So for our next topic, it would be all about scientific notation. But what is scientific notation? It is a way of writing very large or very small numbers. It represents a number as a factor multiplied or divided by a power of 10. In order to do this, there are 3 rules when it comes to converting whole numbers or decimal numbers into scientific notation. Let's start. For rule number 1, it is to move the decimal point until there is 1 non-zero digit on its left side. For example, we have here 7,500, which is then transformed into 7.500. So for whole numbers, we would always start from the very end of the last digit from the right side, moving or shifting from right to left. Okay, so starting from here, 1, 2, 3, we'll be putting the decimal point here, hence giving us 7.500. Another example is 0.02304. So for decimal numbers, we'll be starting from the decimal point, moving from left to right. Starting from here, 1, 2, we'll be putting the decimal point here, giving us 2.23, there should be 0 there, 4. Moving on to rule number 2, after moving the decimal point, we will be adding the times 10 raised to n, where n will represent how many times you move the decimal places until you reach a number with a single non-zero digit on the left side. For example, we move 5 decimal places, so that would be times 10 raised to 5 or negative 5 depending on which direction we moved. For rule number 3, the value of n will be positive if you move the decimal point to the left, while the value of n will be negative if you move the decimal point to the right. So looking at this example here, 7,500, if we start from here, moving from right to left, 1, 2, 3, it would give us 7.5 times 10 raised to positive 3 since we moved the decimal point to the left. Okay, for 0.002234, we will be starting from the decimal point, moving from left to right. So 1, 2, 3. We also move 3 decimal places, so it gives us 2.234 times 10 raised to negative 3 since we moved the decimal point to the right.
After learning the rules on how to convert whole numbers or decimal numbers into scientific notation, here is a sample activity we can try. Starting with letter A, we have 2,700 centimeters. Since it is a whole number, we will be starting from the very end of the last digit from the right side, moving from right to left. Starting from here, 1, 2, 3. So it will give us 2.7 times 10 raised to positive 3 since we moved 3 decimal places to the left. For letter B, we have 0.0000765 millimeters. So for this one, we will be starting from the decimal point, moving from left to right. Starting from here, 1, 2, 3, 4, 5, 6. So we move 6 decimal places to the right. So the answer would be 7.65 times 10 raised to negative 6. For letters C and D, we will be converting the scientific notations back to its regular notation. In doing this, the first thing we should do is to look at the exponent since it will tell us in which direction and how many decimal places we should move the decimal point. Unlike earlier, if the exponent is positive, instead of moving from right to left, we will be moving the decimal point from left to right. On the other hand, if the exponent is negative, instead of moving it from left to right, we will be moving the decimal point from right to left, since we will be converting them back to its original form. Starting with letter C, we have 1.3 times 10 raised to positive 7. Since the exponent is positive, we will be moving the decimal point from left to right. This will be 1, 2, 3, 4, 5, 6, 7, which will give us the answer 13 million kilometers. Lastly, for letter D, we have 6.82701 times 10 raised to negative 4 milliliters. Since the exponent is negative, we will be moving the decimal point from right to left. Starting from the decimal point, we will be moving 4 places to the left. 1, 2, 3, 4. We will be moving the decimal point here, giving us 0.000682701 milliliters. And that would be the end of our discussion about scientific notation.
So let's proceed to the next topic, scalar and vector quantities. So, what is the difference between scalar and vector? So, scalar has only magnitude but has no direction. One-dimensional cannot be resolved as it has exactly the same value regardless of direction. Any changes in scalar quantity is the reflection of change in the magnitude. While vector has both magnitude and direction, can be 1, 2, or 3-dimensional, can reflect either change in direction or magnitude or changes in both, can be resolved in any direction using the sine or cosine adjacent angle. So let's start with scalar. So scalar has mass. Is a scalar quantity containing mass. A mass of 5 kilos does not designate a direction. It just reflects the amount of substance an object has. For example, a mass of 5 kilograms. Temperature is a scalar quantity that is expressed in degrees Celsius or Kelvin. It may offer details regarding substance and temperature. For example, 30 degrees Celsius Fahrenheit. Next is time. Is a scalar quantity determining a point in time without any direction? For example, 5:76 a.m. And fourth sign is distance. Is a scalar quantity that does not include information about the direction in which the distance was covered. For example, is 4 kilometers from to the house. Next is vector quantities. Displacement. Displacement is a vector quantity. It provides you with both the direction and the magnitude of the position and change. For example, 5 meters apart. Next is velocity. Velocity is vector quantity that includes both speed and direction. For example, 10 meters per second north. Let's proceed. Force. Force is a vector quantity that has both magnitude and direction. For example, 50 newtons to the west. And last, momentum. Defined as the product of an object's mass and its velocity. It has both magnitude and direction. For example, 5 kilogram meter per second to the east. That's all.